Our own galaxy, the Milky Way, remains a mystery to us, even though we are inside it. This isn't just about complex details of stellar formation or the evolution of matter, it's about the basics. We still don't know the exact number of stars in our home or even its true shape. For decades, scientists have debated whether our spiral has 2 arms or 4, and only recently have we leaned toward the latter. Studying an object from the inside is like trying to understand the architecture of your house without ever leaving your room, looking only through a single window at the neighbor across the street. One of the most intriguing questions is, how many other galaxies has the Milky Way eaten? Thanks to the Gaia Space Telescope, which just completed its 10-year mission, we have an answer. Gaia performed 3 trillion observations, creating an unprecedented map of the night sky. Analyzing this data, astronomers discovered 30,000 stars moving in a very strange way. They are going the wrong way. It turns out these stellar migrants did not originally belong to our system. Today, we dive deep into Gaia's data to find out exactly how many neighboring worlds fell victim to our galaxy's appetite. Mapping the Milky Way is incredibly difficult due to the abundance of dust and gas that blocks our view, especially toward the central disk. Astronomers call this area the Zone of Avoidance. Visible light cannot penetrate this veil, so scientists must use X-rays to peer beyond the edge of the invisible. Imagine sitting in a bedroom trying to figure out the layout of the entire building, but the walls in front of you are completely opaque. Compounding this is the problem of distance. It is hard to tell if we are seeing a dim star nearby or a giant, bright sun located at a vast distance. To solve the problem of determining distance, astronomers use the parallax method. You can experience it right now. Hold your finger in front of your face, close one eye, then the other. You will notice your finger jumps against the background. The closer the object, the greater this shift. Using simple trigonometry, the exact distance to the target can be calculated. The same principle works in space, but to measure the distance to a far-off star, we need a base much larger than the distance between our eyes. The secret to the Gaia mission's precision lies in expanding this base. The telescope observed stars for 10 years, using Earth's motion around the Sun. Every 6 months, we find ourselves at opposite points of the orbit, allowing us to use the diameter of Earth's orbit as a giant ruler. In accelerated time-lapse, stars can be seen tracing small loops in the sky. In reality, this is not their motion, but a reflection of our own path around the Sun. Thanks to 3 trillion observations, Gaia built the most accurate 3D map, including 2 billion stars. But the telescope didn't just count them, it studied their luminosity, mass, temperature, and chemical composition. The spacecraft houses 2 powerful cameras with a resolution of nearly 1 billion pixels, the most precise in the history of space exploration. Using spectrometers, scientists record the Doppler effect, which reveals the velocity of the stars. Gaia's data analysis allowed scientists to literally win back time and model the history of our galaxy. Researchers noticed strange bumps at the edges of the disk, which became the first key to solving an ancient catastrophe. By studying the motion of 7 million stars, astronomers from the Netherlands discovered a group of 30,000 objects that not only moved differently but also had a unique chemical composition. These were the remnants of another galaxy. This collision happened between 8 and 11 billion years ago. The culprit was a dwarf galaxy named Gaia Enceladus. Models show how its stars initially stayed together before gradually scattering throughout the Milky Way. It is believed that this merger formed the unique features of our home, including the central bar, a feature not found in all spiral galaxies. It turns out the Milky Way is a true serial devourer. Research has revealed traces of at least 6 absorbed systems. And this process has not stopped. The neighboring Sagittarius dwarf galaxy has already collided with ours 3 times in the last 5 billion years and is set to do so again. Remarkably, one of these collisions may have been the spark that ignited our Sun. Eventually, Sagittarius will become the 7th victim whose stars are completely assimilated. Unfortunately, Gaia's active mission time has come to an end. To maintain its position at the Lagrange point, the spacecraft used cold gas microthrusters, but the fuel reserves are exhausted. On January 15, Gaia conducted its final scientific observations and began a final calibration process before powering down completely in March 2025. However, its story is not over. Massive data packets still await publication. The 2026 release will reveal secrets about star movements and the possible locations of new exoplanets. The collected data allows us not only to look into the past but also to model the future millions of years ahead. We see how nearby stars initially move apart and then gather back together under the influence of density waves. These calculations help explain the very nature of our galaxy's spiral arms. Gaia also helped with local matters. It recorded the positions of over 150,000 asteroids in our solar system, discovering that many of them have their own small moons. When we look at photos of distant galaxies, we see majestic, static objects. But how do they actually rotate? The first thing that comes to mind is that they spin around their axis like a solid body. But this is a deep misconception. A galaxy consists of billions of individual stars, each following its own orbit. If they rotated like a rigid structure, the arms would wind into a tight spiral in just a few million years. The leading theory is that the arms are density waves, traffic jams, where stars and gas pass through, slowing down only temporarily. Interestingly, density waves can be observed not only on a galactic scale but also in Saturn's rings. There, the gravity of small shepherd moons creates patterns resembling the annual rings of a tree. On a galactic scale, it is in these zones of increased density that most new stars are born. The arms look brighter not just because of the concentration of matter, but because the hottest, most massive, and shortest-lived blue stars are concentrated there. Another phenomenon of spiral galaxies is related to dark matter. In the early universe, stars on the outskirts should have orbited much slower than those closer to the center. That's what standard gravity dictates. However, today we see stars at the periphery racing at incredible speeds. This happens due to the influence of an invisible halo of dark matter. It acts like an invisible glue, keeping the galaxy from flying apart and forcing its outer parts to move against the laws of classical physics. But in space, there are always rule breakers. Most galaxies rotate predictably, but some, like NGC 4622, have arms that point in the direction of rotation. Another example is the Black Eye galaxy, which has two disks of gas rotating in opposite directions. This is likely the result of a merger with another gas-rich system in the distant past. These rebels remind us that every galaxy's history is unique and full of catastrophic events. Elliptical galaxies represent another major class of stellar systems. Unlike spirals, they contain almost no dust or gas, meaning the process of star formation has practically stopped. In such worlds, stars are independent wanderers moving in elongated orbits in many different directions. There are also intermediate types, lenticular galaxies, which have kept their disk shape but lost their distinct arms. This is a transition stage where a spiral city turns into an aging elliptical metropolis. The universe is full of secrets hidden beyond visible light. Over 1.5 billion objects remained invisible, draped in a veil of cosmic dust. But thanks to the VISTA survey, Visible and Infrared Survey Telescope for Astronomy, we finally lifted this curtain. In September 2024, the most extensive infrared map of the Milky Way was published. Over 13 years, the telescope took images, accumulating data equivalent to 3 years of continuous 4K streaming. VISTA's main advantage is that its vision works at wavelengths that penetrate dust. Where ordinary telescopes see only black smudges, VISTA sees the light of stars and cold brown dwarfs, failed stars that lacked the mass to ignite. Look at the Lobster Nebula. In visible light, it is a dense cloud, but in infrared, the dust disappears, revealing hundreds of thousands of new objects. This map is 10 times larger than any previous catalog, providing a detailed 3D view of the heart of our galaxy. In 2015, VISTA discovered something amazing in the Trifid Nebula, 2 Cepheid variable stars on the opposite side of the galaxy. They are 7 times further away than the nebula itself. Cepheids are cosmic lighthouses that pulse rhythmically, allowing astronomers to calculate distances with incredible precision over tens of millions of light-years. With their help, we build a real picture of the scale of our stellar island. Another discovery was made at the very center of the galactic bulge. Scientists found a group of classical Cepheids there, very young stars, less than 100 million years old. This was a sensation because it was previously thought the center of the Milky Way consisted only of ancient stars. This discovery proves that star formation has not stopped at the center of our home for the last 100 million years. Moving even deeper into history, VISTA found RR Lyrae-type stars right in the center of the Milky Way. These are among the oldest objects in the universe. Their presence there confirms the theory that the central bulge of our galaxy grew through the merger of ancient globular clusters at the dawn of time. Thus, these stars are living witnesses to the turbulent birth of our galactic home. Besides stars, VISTA found dozens of new star clusters that were hidden by cosmic dust. One of them is on the back side of the galaxy, far beyond its center. This work lays the foundation for future missions. We already have the most detailed 3D map in history, and this is just the beginning of understanding how our world evolved. Now, look at deep space images. In the foreground are stars from our galaxy, but in the background are entire stellar islands, each containing billions of suns. Usually, they are seen as blurry spots, but there is an exception: quasars. These are objects so bright they can be seen from billions of light-years away. A quasar is an active supermassive black hole whose accretion disk radiates thousands of times more energy than an entire galaxy. At the center of the Milky Way, there is also a giant, Sagittarius A*, but it is quiet. We are lucky. If it were an active quasar, the powerful radiation could make life on Earth impossible. But tiny versions of these monsters, microquasars, hide right inside our galaxy. They form around ordinary stellar mass black holes and eject powerful jets of matter, accelerating particles to speeds near the speed of light. Studying microquasars brought a surprise: electrons in their jets gain staggering energy by passing repeatedly through magnetic accelerators. This helps us understand the nature of the most massive black holes in the universe. We see giants like TON 618, whose mass is 66 billion suns. We observe it as it was 10 billion years ago. The fact that such monsters existed in such a young universe remains one of the greatest mysteries of science. Over decades of work, the Hubble telescope has shown us the entire scale of galaxy evolution, from turbulent, stellar nurseries, to slowly fading systems. Every collision or merger changes the shape of a galaxy, igniting new stars or, conversely, ejecting gas into the void, condemning the system to a slow fade. Ultimately, we realize the entire universe is not a chaotic collection of objects, but a giant, cosmic web. Galaxies gather into filaments, forming a grandiose structure. Looking at these images, we realize our Milky Way is only a tiny part of an incredibly complex and connected system, the scale of which we are only beginning to grasp. When a galaxy devours its neighbor, it rarely goes unnoticed. Look at ARP 147, a pair resembling the number 10. This is the result of a head-on collision where one galaxy literally passed through another, creating an expanding ring of bright blue newborn stars. Gravity here works like a sculptor, carving new, bizarre shapes out of chaos. There are also tiny systems, like NGC 1569. This galaxy is no larger than the Small Magellanic Cloud, but it is one big stellar nursery. Because of its proximity to massive neighbors, the gas inside is compressed, triggering a starburst 100 times faster than anything in our Milky Way. This is a clear example of how a small system can live life to the fullest. Sometimes we see galaxies that are simply devoid of color and life. NGC 4921 is an anemic spiral where new stars are hardly born. Its arms have turned into a translucent haze. This is a sad end to evolution, where building material runs out, and a once-active metropolis turns into a ghostly shadow of its former self. But gravity can also be a lens. Massive clusters of galaxies warp light so strongly that we see distant objects as stretched arcs. This gravitational lensing allows us to peer into depths of the universe that would be inaccessible even to the most powerful telescopes. It is our natural telescope floating in the void. ARP's catalog of peculiar galaxies is full of freaks, systems that laugh in the face of any order. For example, ARP 116, where a huge elliptical galaxy stands side by side with a graceful spiral. Or the tiny M60 UCD1, the densest galaxy known, where stars are 25 times closer together than in our neighborhood. Galaxy collisions are a process stretched over millions of years. ARP 142, or the penguin and the egg, shows us how gravity pulls entire arms away, turning a spiral structure into a chaotic stellar trail. Eventually, these systems will merge into one, forming a new, more massive structure. The universe on the largest scales resembles a sponge or a neural network. Galaxies are only nodes in a giant cosmic web. Between them lie voids, vast empty spaces hundreds of millions of light-years across. We live on one of the threads of this structure, hurtling through space in an endless dance of gravity. Studying black holes and their influence on the surrounding space opens up physics that is impossible on Earth. Quasar jets, piercing intergalactic space for millions of light-years, are the most powerful particle accelerators in the universe. Understanding these processes is the key to understanding how our reality was born and how it will end. Ultimately, every new discovery from telescopes like Hubble, Gaia, or James Webb makes our world a little clearer, but at the same time raises even more questions. We are but observers on a small planet, trying to decode messages that light has carried to us for billions of years. But it is this drive for knowledge that makes us part of this great cosmic story.